Hi, I'm Sarah, and this is my demonstration for miscellaneous algorithm. Um, First, we start out with the taxi problem, and so we go with the Chinkhate function library, and here we render our environment, so that's how we can display it, and we can get our string. Um, this is essentially showing us that we have 500 states and 6 actions. So the actions were go up, down, left, right, or pick up passenger and drop a passenger. Then this line essentially is just showing us one entry. So that's the of our environment. So that just shows what state we're in and if it's a pick up, drop, all of that. So these are all the possible states we have. Then initially we are showing a random solution for our program. And essentially what this does is it shows us that like we need a reinforcement learning algorithm to do our task for a taxi problem. How we know it's random is through this line. It says action is equal to environment direction dot sample. It selects any random action you want to take, regardless of what if you want to pick up or drop a passenger. After that, here we are just printing the frames and through all of this. So I'll just run that and show you. So once we take random actions and we play that, we can see that the taxi isn't really doing anything. It's just taking a random action. We are supposed to go to Y and to the pink because Y is blue color and blue is our start, pink is our destination, but our taxi is not going anywhere near that. So we can't really rely on our random actions for our taxi problem. I'm going to stop it here. Then so now we're going to start our reinforcement learning based solution. And this is, we're going to create a Q table for that. Now, since we have 6 actions at 500 states, our Q table would be as such. And we're going to go with 1,000 episodes. So this actually takes a really long time to render, and training takes some time as well. I'm going to just run that for you. And it's training. So it's training, and you can see that. And something I added in this code was this total epochs and total penalties so that we could see our reasoning as to why we should use reinforcement learning and what these parameters are for. The alpha learning rate, gamma discount factor, and epsilon was our acceleration rate. So in this code, essentially, we just check, we go for a random number from 0, 1, and we check if it's less than epsilon. So if epsilon is really less, like right now 0.1, it's more likely to take an exploited value, like more likely to choose an action that exploits the state rather than explores. So that's why in our base function we would like our penalties are quite less, so that's good. And the other thing is, so this is trained, and when we render it, so initially I had done this for a lot of time, but now that I render it, it's going to take forever to learn this. But once it does, it slowly begins to learn that we are supposed to get our passenger from our blue letter and drop it off to our pink letter. This can keep on going for a really long time. And once it finishes like rendering, once it finishes training, we can access the Q table values for this function. And this is the Q table values for that particular state. So we can see our taxi now picked up our passenger, but is looking for the drop-off point. And it should find it soon. It found it, but it didn't know it had to drop it off. So it has the passenger, and now it's one complete journey. So as time goes on, it will learn how to do it properly, and we would be seeing the taxi learn quite well. I'm going to pause it right now. So these are my test cases for the taxi problem. I decided to change my values for gamma and alpha. Sorry, for epsilon and alpha. gamma remains the same. So the exploration rate, I increased it so that it decides to take random steps more often than learn steps. And when I did this, as you can see, the penalties were a lot more. And you can play that as well. And for the, this is how it looks like. And for the learning rate, sorry, for my second test case, I decided to go with a higher learning rate, but it exploits more often than it learns. Previously, our exploitation rate was also 0.1, so it was the same. But now we're trying to focus on learning more, on exploiting more. So as you can see, the penalties are quite less, and we've done a good job here. Now, MapReduce function. So this is the MapReduce function that is being given. And what it does is it gets all our, it goes through two files. So it goes through my folder, which has 2 text files and 1 image file. The image file was this image right here. And after that, it went through these 2 text files and counted every single word, like the frequency for those words. And now after the whole map and reducing thing, we can get which what the frequency of the words are separately as well. So for my code, I did matrix multiplication as suggested by the taxi. And these are the 2 matrices I decided to use. One is 2 by 3, and one is a 3 by 2. And here I went for coordinates. Here I got the coordinates for my first matrix. That's matrix M. And this is the coordinates for matrix N. The main difference here is that the rows and columns are switched. So J over here is the columns, but J here is the rows. Then, okay. Now we begin mapping. So essentially why we are using mapping is so that we can distribute our data into different checkout points or like processing points. So we don't want one function to use the same processing of same function. So like I described in my report, I gave the example of airport security. So as you can see in this, when there's a lot of people who want to get checked into the airplane, they would go into different counters, and that makes the entire process a lot easier. So that everyone's getting handled. I mean, even if the security counters are doing the same job, they're still helping everybody by getting through the lines earlier. And so that's what this is trying to do. So we have a lot of data, and we're putting them to these 2 map functions. So the first map function is returning a pair of it's returning a key value pair. Second, for the second matrix, it's also returning a key value pair. The same reason as stated here, because our rows and columns are different. So that's a big thing. Rows and columns for J. So J over here means different than J here. After that, we go, this is done. After that, we reduce it. So now we have 2 different pairs of 2 different key value pair lists. So I'm returning this as a list in my map. And initializing a list, I'm separating out the coordinates that I got from the previous function, this function, and I'm separating them here, and I'm putting them back into our required formats. So that was J, M, I, and MJ. So J was our which row we are at, M was the identifier, I is our column, and this was our element. And for here, I is our for here, J was our column, M was again our identifier, I was our row, and that's our element. Then reduce step, what it does is it combines everything. So we take in the outputs of these 2 functions and we put it here, and then we get our product. So we multiply it. We make sure that our J is the same. Our row and our column that is required needs to be the same, otherwise it's going to throw a lot of errors. After that, we append it into another key value pair. So there's a lot of key value pairs happening, and it returns that key value pair. Then it goes into the next step. This is for identification, and you just bring in an element and it will match up with the pair and it will give you the pair. Now reduce step 2. This finalizes everything. It adds up all our whatever we multiplied, it just adds up and it gives us our final result. So this is our final result of our matrix multiplication. Now map and reduce. So for the second one, I decided to go with matrix vector multiplication. And here we have our matrix. Here we have our matrix, and here we have our vector. And we need to have our matrix and our vector of the same n. So if our vector is of length 2, then we need to have a matrix of 2 by 2. And coordinates for our matrix is the same as the above function used, but coordinates for vector changes a bit. And here we are, our j is going to be our column. These are our coordinates that we get. Now we have only one map and one reduce in matrix and vector multiplication. So that's what it does. So it iterates over through the coordinates of the vector. It gets the j, k, and our elements according to our coordinates. And after that, it iterates over all our coordinates in our matrix list, our matrix key value pair, and then it gets our I, j, and elements. So that's done by these steps, and then we just equate. We make sure we're equating it to the correct j, so to the correct row, and then we get our product. So we multiply our two elements, and then we append it into another key value pair. So that's also into another list in this format. Once that's done, we reduce it. So whatever our output goes here. We get a dictionary. For this is similar to the reduce function I've used for matrix and matrix. So I get a dictionary. I initialize it, and I say that if in the pairs that I have given it, if for all of them, iterating all of them, I just take the first element. So that would be the key. So that would be our I, comma k, and I would check if it's in the dictionary. Then just if it's in the dictionary, then I should just add it and add the element to it. And whatever existing value that key has, just add the new value in it. If it's not, just add it in the dictionary. So add the new one, or if it already exists, then whatever new value this new element in the list is bringing, just add it to the existing value in our dictionary. And then after we run it, we can see that this is our desired output, and we're getting what we want in our code. So that's my that's for my program, and in my report as well, I've solved all the questions. And this is for Monte Carlo, explaining Monte Carlo, giving a small algorithm or pseudocode. I wrote a small pseudocode for it, and I explained why AlphaGo beat the player in the game of Go. And I've done my reflection. So I hope that's up to the par, and thank you so much for listening.